Today, function notation. Function notation. Yours says 3.2 on the note, though, doesn't it? Yeah, okay, so that yours is fixed up so that you can match it up with the homework. Yes? Consider this problem here. Hopefully this problem seems very familiar to you. Fezzik has a job selling stereos. He makes $150 per week plus $20 for each stereo he sells. How much money does Fezzik make in a total each week? You're supposed to have ran into this type of problem in grade 9 and grade 10. It's a regular linear type problem. The reason it's linear is because he makes $20 for each stereo. It goes up in a straight line. We're supposed to have beat that to death, but if we haven't, I'm reteaching it like maybe you don't really remember, okay? So, the first thing you should notice is I can't answer this question until you tell me how many stereos he sold. If I just give this question, $150 per week plus 20 for each stereo he sells, you'd be like, well, how much does he make? I can't possibly know that. There's no way I can figure that out till you tell me how many stereos. In these scenarios, what we do is we make up an equation. That's really what we're going to be about here, okay? We can set up an equation or a function. Again, if you left yesterday's note or you were away yesterday, one of the things I talked about is we've been doing functions the whole time. Y equals mx plus b, all those lines, those were a type of function. All the quadratics, y equals x squared, and all that factoring and quadratic formula stuff we did, that was all working on another type of function, x squared. And now we just generalized it to say functions can be represented by equations. Y equals something. The only rule is every x value can only have one y value. Do you agree by looking at this? It's going to be a function. Once we figure out how many stereos he sold, like 5, he's not going to get 2 different answers for how much he makes. For every number of stereos, there's one pay he gets. He doesn't get different kinds of pay. So we can set up a function or an equation. Hopefully you're not going to be surprised, even if right now you're like, I don't know if I could make the equation for this. Hopefully when I make the equation, you're going to be like, oh yeah, that one I know. I know how to do that one. So once we have an input for the function, number of stereos sold, we can give the output, amount of money made. So let's set up the 2 variables involved. You could use x here, and if you're still attached to x, then you should go ahead and use it whenever you want. Moving forward, we'll try and be a little smarter about the variables we choose, because x being number of stereos doesn't really, that's not really awesome. Like, it's not the perfect choice. Where n for number of stereos or s for number of stereos would be better logical choices. Me personally, my writing, me and s, I got to be careful with s's because I draw them too fast and they look like 5s. So I often don't use s. Look at right on the board there. Look at that. My 5s are lazy. I don't go over, down, around, and so then I get messed up. But again, that doesn't mean it has to mess you up. Maybe your s's are beautiful, and then you could use s in this situation. I used n. And p represent the amount of money he made in a week. Why p? P for pay, I guess, but you could use m for money if that makes more sense to you. We can now write the function as, I hope this looks familiar. P at n equals 150, that's how much he gets no matter what, plus $20 times the number of stereos. Now I've done a bunch of stuff to tweak you already in the 3rd slide of this to make your brain go, what's happening, what's happening? Because in grade 9, we wouldn't have called that P at n, we would have called that y. And this would have been y equals mx plus b, but look it's the other way around, isn't it? No different, except when we talk about this situation, it really feels like 150 should be first. I get 150 plus I get $20 per stereo. Now I'm going to write what you would have done underneath to really try to help and make you go, oh, okay, this is no big deal. I'm going to try and write this underneath in a color that comes up good. Yellow. Acting like this exact same problem. If this exact same problem was in grade 9, you would have wrote y equals 20x plus 150. That's what you would have done in grade 9 with the exact same problem. Because you would have said, oh, it's going up by 20s, so y equals 20x, and it starts at 150. So I'm not trying to change the equation. I'm trying to change how we write the equation. Question?
Why is that Pn and not just P?
Oh, it could be P. Yeah, that's exactly, okay, he's asking the perfect question. And maybe it's possible the only question of the day. Why did you write P at n there? Because going back to here, this lesson's called function notation. My whole job today, every dollar they're paying me today, is for this moment to explain what this means, P at n, okay? So if you've only got 3.5 minutes of attention span to use today, use it right now. It wouldn't be wrong to write P. It just wouldn't be in what we call function notation. Function notation looks like this. It's got P with an n there. And what this is saying when we write P at n is it's fixing a lie we might have told you. I might have told it to some of you. I would have said something like, when you write a letter beside another letter, that means multiply. In chapter 1, I might have said that out loud to you. I might have said, when you write two letters beside each other in math, we mean multiply. And the reason we do it is because if we write a multiply symbol, it'll look like X. So we really try to let go of the multiply symbol. We only use it once in a while because it looks like an X. It's just confusing. So at some point we decided, don't use multiply symbol if you don't have to. And then, as I lied to you in chapter 1, and you said, oh, what happens when it's X beside Y? And I said, well, it's always multiply when there's two letters beside each other. I knew it. As I was saying, I'm like, I'm going to have to fix this later. But we have to get through chapter 1, so it's a good rule overall. But in function notation, like this, P with an n inside means something different. It means, oh, listen to this sentence, why this is difficult. This sentence means, I'm looking for an equation for P. To get P, the pay, I'm going to have to sub in an n. So there's going to be an n I'll sub in. So you got to tell me the n, then I can get the p. So this symbol means a lot more than just p equals. It's describing what's going on here. Coming next is a equation where you're going to need n. So if you want, you can stop there and go, you're going to need n here. Is it clear? It's like a warning sign. Be clear, you're going to need n. You're going to need to figure out what n is to be able to solve this equation. Got it? Okay, now we go. So if I just wrote p, the equation could be anything. But when I write P at n, I mean this is going to have n's in it specifically. Yeah? This one at the bottom, you'll see it written in later grades as y at x, like that. Exact same situation, but they're warning people there's an x coming. Now, the reason we don't write it with y is because lots of times when we're using y, x is coming and everybody goes, you don't have to write y at x. I know y and x often travel together. But when you're doing P, maybe it's P at X. Maybe it's P at T. Maybe it's P at R. It depends on what you're doing. This one's saying P at N. So that N is just a placeholder to say, watch out, N coming. But it's the right question. And look, how long did that take? It took me 3 minutes to explain why there's an N in there. But that's what the lesson's called, function notation. So I'm going to go back to the first slide and add some stuff. Maybe you should go back to the first slide. And maybe this explains what the lesson's about. Pointer options. Oh, I need my touch screen. Pointer options. Ink color. I want that pink, that yellow. I didn't get the yellow last time. Do it with my mouse. I want this on your screen, or on your page. Ink color. Yellow. Now it's good. Here's the whole lesson in a nutshell. We want to take something like this, y equals 5x minus 3, and we're going to learn to write it the exact same thing as, say, p at n equals 5n minus 3. And it's okay right now to be frustrated with me and go, why are you changing it? We did all that work on y equals mx plus b, and you're changing it. I'm changing it when we need to, when we need a more powerful notation. And it won't become super clear for a while why this has advantages over that. But again, I'll say the real big deal is when I write y equals, I don't know what's coming next. When I write p at n equals, I know what's coming next. An equation that has n in it.
Why'd you write the n before the -3 when down here you wrote the 150 before the 20n?
Oh yeah, okay, now, next question is about linear functions. When we're reading in grade 9, we pounded away on this idea that put the slope there and the number there. And what we were trying to teach was graphing, so people could look at y equals mx plus b and know where they go. It just happened that in this description, it would be awfully tempting for someone who wasn't thinking about y equals mx plus b, who was looking at this going, okay, we start with 150, and then we make $20 per stereo. So it would be awfully tempting just to, out of the way it was written, to write the 150 first. But it really doesn't matter which way you write it. It's just another way of thinking. 150 plus 20n is the same as 20n plus 150. So if right now you're like, you're just playing with the labels here. You're not really teaching any new math. You're just giving things new labels. That's true. We're stopping for a second, building what's called function notation, which will help us to do future problems. Okay? That's hard. It's hard to trust the math teacher that what we're building is going to matter and that I'm not just relabeling things to confuse you. Because you certainly could feel that way right now, that I'm just making new labels and confusing the issue. So a little bit more about this. P at n equals 150 plus 20n. This is read P at n. And I've been doing that all the way along, but it's important to have it written down in there so when you look at it and I say P at n, you know what I mean. We can interpret this expression as the amount of money made for selling n stereos. That's how it's different. Evan asked, why is P different than P at n? Well, he phrased it differently than that. But that's what he was asking, is why do you want P at n? Because P at n adds a little more to the story. P at n says, you need to know the number of stereos here. Evan argues, so did P equals. I just had to look over here to see what variables are involved there. I know, but there's a difference. The difference is having it there on the left side allows me to know what I'm talking about. And you are welcome to be a little bit frustrated by how this is played out. It is played out badly. Anyone taking chemistry right now? You're about to get frustrated, I think. The story before was little electrons fly around the center in little orbits just like solar systems. And then later on she's going to go, well, it's not really like that. And then the story gets changed a little bit. And it's unfortunate. That's how we're sometimes stuck with teaching, is giving you a basic version of something and then improving on it later. That's what I'm doing. I'm taking y equals mx plus b and I'm trying to improve on it. I'm trying to make it better. So this notation does not mean p times n, and it's okay, again, if you look at me and go, Mr. Todd, you said when there's two letters beside each other, it means multiply. I'm like, I know. Maybe I didn't lie. I left out part of the story. I didn't say, unless we're doing functions, and when it's functions, this doesn't mean p times n. It means p with n subbed in is another way of saying that. I see people still writing, so I'm... Do you need more time?
Yeah.
Oh, yeah. All right. Good. I'm glad you're copying it all down because this, I mean, if you're only going to tune in for one slide today, this might be the slide. This is the slide that goes, okay, new way of writing this. P at n doesn't mean p times n. Besides that, it works all the same. We're just going to sub into it. After this, the rest of the lesson, we're just going to be subbing in, which is, we've done subbing in before. It's good? All right. We're good? We're happy. So, if all of that leaves you going, I don't really know exactly what you're saying. Okay, I can write different letters if you want, but I don't really know what's happening. Let's just talk about functions for a minute and another way to think about them. Using our exciting new notation, we can picture functions as a machine. Yes? So here's a new definition of functions. A function is a machine that gives a single output for every valid input. This is exactly what machines do. If I had a machine, some kind of construction thing that was assembling something, and I put in some metal, out the other side, a bicycle comes out. Not that fast, but you get the idea. One bicycle, not multiple things. One thing comes out of the machine. Yes? That's a good way to visualize what's happening. My favorite one is this one on the bottom right here, this little blue drill thing. Yeah? You send in a computer board or a frying pan or whatever. It does some work on it, and out comes something. That's what a function does. A function takes a number like x or 2 or 7 and turns it into a different number. Yes? Welcome to the machine. Yes? You'll have to watch this once to decide what you're going to write on your slide. Here's what we mean by that. We have a function f. Along comes x, and we take x and plug it into the function. I'm going to replay this again, so you can watch it once and then decide what you're going to write. The machine does some thinking. Maybe it multiplies by 3. Maybe it adds 7. Maybe it takes square root. How will we know? We'll have an equation. The equation will tell us what to do here, and we'll do that work. And what comes out is the answer, and the answer is f at x. It's the function having operated on x. I'm going to play it again and talk about it again. A good way to picture functions is a machine. We're going to be given an x value, and that x value we're going to plug into the function. We're going to let the function do its operations, and they might be multiplied, divide, square root, squared, all these things that might happen. After subbing that number in, out's going to come an answer, and we're going to call that answer f at x. That is, what is the function value after x has operated? Now, my experience tells me that that sort of helps. Sort of helps. Not really. Olivia says, no, not really. But now I'm going to do it with numbers. I'm going to actually put numbers in, and maybe you'll go, oh, I see what you mean by plug it in. So the exact same example, except I'm telling you what f at x is. And it's an f at x that's familiar. It's straight out of grade 9. It's 2x plus 3. What happens? They come along with an x value. What happens when x equals 5? And again, I'm going to play this twice. So the first time through, you're just watching to go, how am I going to write this down? Okay, that's okay. Just watch it once. X equals 5. I'm going to take in and sub it in, and you know how to do that. If x is 5, we're going to go 2 times 5 plus 3. You can use your calculator, or hopefully you can do 2 times 5 plus 3 in your head. 2 times 5 is 10, plus 3 is 13. After all that work gets done, I get an answer of 13. And this slide is not trying to do the algebra. I got one more slide after this where it's like, okay, let's do the algebra. Because I don't expect you in your homework to draw a function machine. Draw arrows going into it. Draw swirlies in the middle. That's not how we're going to do the homework. The last slide is how we do the homework. One more time through the slide. If you had a function 2x plus 3, and you wanted to sub in x equals 5, you'd take the 5, and you would sub it into the function machine. Hopefully you know what to do there. You replace x with 5. You go 2 times 5 plus 3, and the end result is f at 5 equals 13. I don't know. You can write it how you want. I think I'd probably write x equals 5 up here. Then an arrow into here, right to there, into where that x is. And then an arrow saying, after that's done, I get 13. Hopefully, I chose a function that you don't really need your calculator for. You go, I get it. 2 times 5 plus 3 is 13. But before you give up and decide you don't get it, we'll do it one more time without the crazy animation with how you're going to write it. But Olivia has a question. Tell me.
Is there like, are we going to get to a point where we get rid of f and like multiply 5 in, because we're just adding the x in, so we're not doing anything with it?
You're right, we're not doing anything with that x there. We're just putting 5 in there. So f at x equals 2x plus 3 is like a situation where it's saying, listen, if you want to get f values, y values, you're going to need the x value. You go, I got an x value. I'm like, okay, good. I just wanted to warn you. F at x is like, I just wanted to warn you. You better have an x. Yeah, okay, I got an x. And then what do you do to get that? You sub the 5 in, and you go 2 times 5 is 3. So that means f, when you put in 5, was 13. So this is saying all that stuff. It's saying f, when you put in 5, is 13. Here, that's a good sentence. I'm going to write underneath. F, when you sub in 5 is 13. That's why that's so weird looking, because it's a whole sentence of what's being described there. When you sub in 5, you get answer 13. That's what f at 5 equals 13 means. But again, this next slide is where we find out where we're at. After all that explanation, after me building all this house of cards, this Lego tower, this next one is like the one that goes, oh, I got it. I see what you're trying to say. Yeah? This is what decides it. An example without the cheesy animation. If f at x equals 3x plus 4, find f at 2. There's a lot going on here. It says f at x, which it says, if you want to know the answer here, you better have the x value. You're going to need an x value. Okay? They said f at 2. He says, oh, I know the x value. 2. They want me to sub in 2. And then the function says, oh, okay. If you know the x value, just put the 2 in there right here. So when we write it, we write f at x equals 3x plus 4. And we go, okay, I know I want 2, so I put 2 in here. That means f when I sub in 2 is 3 times 2 plus 4. Hopefully you can do that mathematics. Hopefully that's the least difficult part of the day. 3 times 2 is 6 plus 4 is 10. Answer, f at 2 equals 10. And that's it for now. And it's okay if you're like, what are we doing with this? Where are we going with this? Yeah, absolutely. We got a long way to go with this. The course is called Functions. There's not going to just be one lesson on functions. It's just like, let's just start playing around with these a little bit. What can we do with these? And for today, it's, oh, just sub some numbers in. So when x equals 2, f at 2 came out to be 10. Now, if you're really lost, if you're like, this is all going right on past me, I'm going to write an extra sentence here in brackets. Don't write it unless you need it, but if you do need it, rely on this for now. What this is saying is, when x equals 2, the y value comes out to be 10. It's okay right now to go, so you're writing f for y? That's why I came in today? You're writing f for y? That's a very basic understanding of what's happening, but it'll get you through. You'll be okay if you just go, okay, I'm just getting the y value. That's all I'm doing is subbing in the x value to get the y value. And I mentioned that in the last slide again. No, on the next slide. Do you need more time? So, equations and function notation. Any equation that is a function can be written using function notation. For example, last year in grade 10, all the time you would have done y equals x squared minus 4x plus 7. I'm suggesting that we could write the exact same xy equation using our new function notation. We would just write f at x equals x squared minus 4x plus 7. And it is totally fine right now to be like, so where you see y, you're just writing f at x? Why are you making it more complicated? There's lots of good reasons why I'm doing it. But today it's okay to go, okay, so instead of writing y, I just write f at x. Okay. I guess I'll play along to see how this story turns out. You didn't have to copy anything there, did you? Notice the symbol f at x is another name for y. It's deeper than that, but it's okay. That's okay for now if that's where you want to live. But with graphs, I say it's actually easier. There's a function f at x. This will have a very complicated equation. You see, it's not a parabola. It's got a little more to it. We'll get to, in advanced functions, we'll get to being able to make equations like this. And they're not that bad. They're not that crazy. But anyways, from the graph, y equals f at x, find f at negative 2. Which means find y when x equals negative 2. I think you should write that down. Because that's where your question's going to be in all this is, what does f at negative 2 even mean? And it means find y when x equals negative 2. Once you have that, then your problems are sort of over. You go over the graph and go, okay, negative 2. I got to look at this graph carefully. Negative 1, 2, 3, 4. Oh, so there's negative 1 right there. Let me write that on there. That's negative 1. I don't like this color anymore on the graph, so I'm going to try to switch to, let's see, maybe something in red. There. Negative 1, negative 2. They want to know at negative 2, what answer do I get? 40. F at negative 2 appears to be 40. I say appears, I'm not trying to be tricky. You might look at the graph and go, is it exactly 40? Is it a little above 40? Is it a little below 40? No, it just seems to be 40. Seeing that, does anyone want to take a shot at F at 5? What it is approximately. Evan, what do you got?
Negative 10.
Looks like about,
Oh, wait. F at 5?
F at
Oh,
5.
like negative 15.
About negative, appears to be about negative 15. Because you look over at the x value of 5, and it looks like about y value negative 15. So off the graphs, you're just looking to see what y value you get when x equals 5. So I went over to x equals 5 here, and I said, okay, what y value do I get on the graph? Right there. And maybe I'll even write the coordinates there. That's 5 comma negative 15. That's what that point is. So that means when x equals 5, y is negative 15. So reading it off the graphs is just a matter of using the x value given to find the y value given. You don't have to put it into an equation. Most people like the equations better, though. I'd rather just sub in than try and work out what's on this graph. But we'll need to be able to do both. Do you have any questions on that? I don't know that that lesson should be considered one that when I'm done, on a scale of 1 to 100, you feel 100% confident. I feel like maybe our goal in that lesson is like, I feel 65% confident. I sort of get what you're saying, but I better take a look at this homework. So it's important that you really do take a look at this homework and go, can I do what he's saying? Because if you get it, it's really straightforward. But if you don't get it, it's like you don't even know what it's talking about. So then you'll definitely have to ask me questions about that.